Neutrinos are remarkable, unique particles. They are remarkable because neutrinos are particles fill up the universe by an enormous amount.
They are, in a sense, the simplest expression of matter that we know it exists.
There's the electron, the muon, and tau particle, and each one of those has a partner neutral particle called a neutrino.
Neutrinos are chargeless, but they do have mass. Because of this mass component of the neutrino, when a neutrino is created at one point, when it is detected at some other point, we see that we are detecting a different flavor of neutrino, and that is neutrino oscillation. SBN program, that is the Short-Baseline Neutrino Program at Fermilab, it's a group of detectors, one being the near detector, another being the far detector, which sits at some far distance from the beam target. They sit on the same neutrino beam line, so they see the same neutrino energy.
So Icarus, as part of what we call the Short-Baseline Neutrino Program, we're looking at the possibility that there could be additional types of neutrinos, so it would be a new type of physics. And we call these things sterile neutrinos because they don't interact with ordinary matter. They only interact with other neutrinos. And so the Icarus detector is located 600 meters from our source of neutrinos, so we can look to see how many of each type of neutrino we have there. However, we also need to make sure we know what types of neutrinos there were at the source.
So the first detector is SBND, and that detector measures the characteristics of the beam just immediately after production. So from the comparison between the two experiments, the one that is close to the source and the one that is farther away, which is Icarus, we can say how many electroneutrinos we should see at the far location. So if we see an excess of electroneutrinos in the beam, there is an anomaly.
And this is very, very important if we want to do a search for sterile neutrino.
Before coming to Fermilab, the Icarus experiment was run for a total of about 3.5 years in Gran Sasso.
So the Icarus detector, it was a new technology about 20 years ago called a liquid argon time projection chamber. And they built the Icarus detector in Italy and installed it in what's called the Gran Sasso National Laboratory.
It took data between 2010 and 2013. At that point, we wanted Icarus to have a second life.
There's two separate detectors. Those were moved to CERN in about 2015. They were disassembled, refurbished, had new components added to them, new components constructed.
In 2017, we started moving everything at Fermilab.
So they were delivered here in 2017, and we had to do some final preparation for them before they could be installed. The building actually was constructed so that you could take part of the end wall of the building off so you could insert it into the building. It took about 1.5 years from there to the point that we had actually fully commissioned all the components.
And in 2020, it started commissioning. And liquid argon was filled.
And so late in August of 2020 is when we turned on the high voltage on the detector and saw our first tracks in the detector.
And we just completed 5 years of operations.
We reached 5 years of continuous operation, not a single glitch. So we created an infrastructure, teams of people that have the ability to continuously look, to follow the experiment.
In terms of physics runs, Icarus started its first physics run in July 2022. We concluded 4 years of physics run.
And we expect to have another 3, altogether with the near detector that came into operation last year, so that we can then combine our observation and get a result. Is the sterile neutrino there or not? This is our target, our #1 goal. So the main technical challenge that we had during operation was the purity of the argon.
The importance of argon is that if you produce argon to a very high purity, and now we are talking about purity of the order of 1 part per trillion, the liquid argon allows you to see tracks and images which are very easy to reconstruct, and therefore the amount of information you can collect with argon is absolutely unique.
Electron neutrino creates showers, but photons also creates showers. But now liquid argon detector technology, it has that ability to distinguish between photon shower and an electron shower.
Fermilab has decided to elect neutrino physics and the argon as the main element of a progress of the whole laboratory. And therefore, for us, it's a great pleasure, a great honor to be allowed to be there, give our little contribution to this very vast program, which is worldwide, of producing new images, new view, new situation about the universe and its characteristics.
So DUNE is a long baseline experiment that is conceptually the same, but the propagation length, instead of being a few hundred meters, is 1,400 kilometers.
And the same technology is being used for the DUNE far detectors and the DUNE near detector. They are learning from both the Icarus experiment and the short baseline near detector to develop even better versions for the DUNE detectors. And they're learning both on the hardware side technology, but also in terms of using AI tools to do that image reconstruction. All those things go towards learning how to do the same kind of thing at DUNE.
This is why neutrino experiments are so important, because by letting neutrino travel over distances over thousands of kilometers, we can understand more clearly what is the mechanism behind neutrinos. And therefore, it becomes from a story of a single experiment to a story of a big program, which is now today the program that Fermilab will do in the next 10 or 15 years. In fact, in the long run, you can say very simply that the progress of science is also the progress of society.